This is the Yaesu FTR-5410 UHF repeater that I did a video on a while back. I had to repair it. This was another Hamfest find. And I got it working. Now this unit is crystal controlled, and it came with crystals for repeater frequency. And I looked on the repeater directory, and this frequency, I've got a repeater on this frequency about 45 miles north of me, and I've got one southeast of me down near Chicago that is about 92 miles, I believe it is. So obviously I'm going to have to change the frequencies here. I don't want to use crystals, so my plan is to use an external synthesizer to apply the carrier oscillator and the receive first mixer frequency to this unit. This unit is crystal controlled. In the receiver here, here's the receive crystal, and in the transmitter, here's the transmit carrier oscillator crystal that controls the carrier here. You can see also there's wires coming up to these. These go to a resistor. It's just a positive temperature coefficient resistor for temperature stability. What I plan on doing is I'm going to remove this crystal and inject an external signal for the carrier oscillator for the transmitter in here, and at the same time another frequency for the receive first mixer frequency. I'll remove this crystal and inject that frequency into the input here. What I plan on doing is generating those frequencies using an SI5351 clock module that is controlled by an Arduino Nano. I was going to mount that circuit inside of the repeater, but I think what I'm going to try, I'll have two external jacks here where I'll have one for the transmit oscillator and one for the receive oscillator here. Those frequencies will be generated externally and then applied to the input here. And then if I want to change frequencies, all I have to do is run the program and then change the frequencies using the software. So that's the plan anyway. What I'll have to do is slight modifications to this unit. What will be nice about this arrangement is I can change the frequencies of both the transmit and receive to any frequencies I want just by running the program and using software to change the frequency of the clock module instead of buying crystals. I've been looking in the repeater directories, and I want to find a repeater pair, a UHF pair, that isn't anywhere near my geographical location here. This will probably not be a coordinated repeater, so if it causes any interference, of course, I'll have to take it off the air. What I'm going to do is when I find those frequencies that I want to use, I'm going to program them into a receiver and sit it on that frequency, and then I will monitor the frequency to see if I get any signals. And I'll probably have a recorder that will be activated by the squelch, so if something comes up on that frequency, I should be able to catch it. That way I'll avoid any possible interference problems. And if there is, like I say, it'll be easy to change the frequency just using the software. And then once that's done, I'll have to dig out my duplexers and then tune those for whatever frequency I'm using here. One of the hurdles I think I'm going to have is I'm going to have to first of all make sure that this oscillators that I'm using in this clock module are stable enough to be used in a transmitter and receiver. And I'm really not sure yet if using the crystal on that clock module is going to be accurate enough. I may have to come up with a different source to drive that clock module that's more stable than the one that's in there. I don't know how that's gonna work out. I have to do that by experimentation. And another problem will be the output of the clock module is going to be a pretty dirty signal. It's going to be basically a square wave, so there'll be a fundamental with a lot of harmonics in it. So I'll have to run the output through some type of bandpass filter to clean up the signal before they're injected into the receiver and the transmitter. So that's the plan, and we'll see how it works. This is what I'll be using to do this experiment and project here. The heart of it will be this clock module. It's based on the SI-5351 clock module, and this basically can generate 3 separate frequencies on these outputs, clock 0, 1, and 2. I'll be using clock 0 and 1. And it's controlled by an Arduino. Here I have an Arduino Nano, and the I2C bus is connected here, and that controls the clock module. And of course it derives its power from the Arduino. The only reason I can do this project is luckily a man called Jason, I think it's Jason Mildrum, came up with this program. And pretty nice program here that he shares it with everybody to control this chip. And anyway, here you see clock 0 and clock 1. You can set your frequency, 2 separate frequencies on different frequencies on these different outputs here, and you can program it to output those frequencies on, in my case, these 2 outputs here, and I'll be using them to drive the receiver and the transmit oscillators directly through possibly through a filter of some type. So anyway, that's what this project's going to be about, and hopefully we'll get this this old repeater back on the air. This is the data sheet for the SI-5351A. I'll be using the A flavor of this chip here in the unit I'm using, and it's made by Silicon Labs. This is the A unit here. And then going down, you can download the data sheet on this if you're interested. Going down through some of the specs, if we finally get to the, let's see, here we go. Alright, here's the SI-5351A, and I'll be using the clock 0 output and the clock 1 output to generate the carrier oscillator for the transmitter and the first local oscillator frequency for the receiver. And basically what this does is the SDA and SCL, this is a I2C bus that's connected to the Arduino, which would be over here, and then I use an Arduino Nano. The frequencies generated by this are not going to be up on the VHF, of course, because I'll be injecting them into a transceiver where that frequency is multiplied quite a bit. So I'll be injecting a fairly low frequency. Well, obviously this frequency is too dirty to be put into the input of a transceiver. I'm going to limit the bandwidth and see if it improves a little bit. We'll drop it down to 20 megahertz. Okay, it's still not a sine wave, but it's getting better. So I think if I run this signal through a bandpass filter, I can get this closer to a sine wave, which I'm going to want a fairly clean signal. Now when I inject this, there are going to be, depending on where I inject it in the circuit, there's going to be some coupling devices that are tuned, so that's going to help to improve this waveform, so it'll be acceptable to be injected into the unit here. Clock 0, I've got it programmed for 12 megahertz, and there's, you can see it's 12 megahertz there. Very lousy looking waveform. And I'm measuring on the scope directly on the output of clock 0 here. I've built just a crude little low pass filter here using an inductor. I think this is a couple microhenries. I forget what this is, 47 picofarads, I think. But anyway, I'm going to look at the waveform. I'm going to go to the output. And you can see it's cleaned it up quite a bit. It's still got some distortion. You can see at the extremes here. But just with a simple two-pole filter here, L filter, LC filter, it has cleaned it up quite a bit. So I think if I add another section here, I might be able to clean it up even more. I need to attenuate the harmonics on here before I inject it into the oscillator chains in the transceiver. Let's say as a hypothetical I wanted to put this repeater on 443.15, 448.15. What I'd have to do is feed the transmit oscillator with 36.92916. This is the formula for the transmit frequency. And 36.2916. I basically got it there. The receive frequency to receive on 448.15, I'd need an oscillator frequency of 47.416 and 47.416. I got that one on clock 0. So clock 0 would feed the receiver and clock 1 would feed the transmitter. And then of course I can program using the Arduino Uno, I can program the frequencies. So basically what I'll have to do, run these two outputs into bandpass filters, clean up the signal, make a nice looking sine wave, and then I'll feed it into the input of the transceiver, and hopefully that'll work. I don't see why it won't. So that will be one of our next steps. Here's what I plan on doing. This is the oscillator of the first mixer that feeds the first mixer in the receiver, and this crystal here is the crystal that generates that frequency. So what my plan is to remove the crystal and inject the signal from my synthesized signal into the chain at this point here. In the output of the oscillator here, there's a tripler in Q04, and that signal is tripled again in Q05. So the signal applied here is multiplied 9 times before being fed up here to the first mixer, Q02. It's fed up to the gate, upper gate here of that mixer here. Now here's the transmitter. This is a carrier oscillator here. Here's the crystal that controls it. It has a posistor here, which just is for temperature stability. This is a control to help keep the temperature stable of the crystal. But anyway, I'm going to remove the crystal and I'll inject the carrier frequency in at this point. And the output of that is buffered by Q02, and then it's doubled in Q03, it's doubled again in Q04, and then it's tripled in Q05. And then that's, at that point, it's up at the output frequency, the UHF frequency. The actual frequency modulation is done in this varactor diode here. So I should be able to inject the carrier oscillator signal here, and of course it goes through the buffer amp, and then it's modulated here. So there shouldn't be a problem as far as I can see. I guess we'll find out when I actually build the circuitry. But the SI chip will be able to generate both my receive local oscillator frequency for the first LO, which generates the first IF, and it will also be able to generate the carrier oscillator frequency for the transmitter here, using the two ports, clock 0 and clock 1, on the output of the SI chip. Okay, the repeater is crystalled for 448.675 megahertz, and I'm going to, in this experiment, I am going to use 443.15, 448.15, so the receive will be on 448.150, and that would give me a crystal frequency, or in this case the oscillator injection frequency, of 47.416. So I've programmed 47.416 megahertz into clock 0, which is this output, coming through the low pass filter and injecting into the crystal socket. I'm monitoring at a test point here. I have a handy turkey on 448.150. Testing, 1, 2, 3, test. Hello, test. And it is retransmitting. Hello, test, 1, 2, 3, test, 1, 2, 3. And then there's a slight delay for the dropout of the transmitter. So with this arrangement, I'll be able to program any frequencies I want on this repeater using the two outputs, clock 0 and clock 1. I can generate the receive oscillator frequency and the transmit oscillator frequency. And since in the transmitter the oscillator isn't modulated, it has a varactor diode down the chain, I can inject a CW signal into the input of the transmit chain, and then it will be modulated, and then it'll be multiplied up to the output frequency. So this transceiver is no longer rock bound, so I'll be able to remove the crystals. Well, now that I know this concept works, I'm going to build another filter. I'll feed the input of the transmitter, and this should work since the oscillator isn't modulated in this unit. And then I'm going to build a shielded low-pass filter that will drive. I think what I'll do is put two connectors on the back here, maybe SMA connectors, and then I'll feed the receive, oscillate, and the transmit oscillate frequencies in through the back here, and then have the clock module as a separate unit. And then what I can do using the software here, I can program whatever frequencies I want. Of course, then I'll have to touch up the these helical resonators here, and the transmitter will have to be peaked. Will have to be tuned, but should work all right. I am going to put it on a spectrum analyzer and look at it and make sure, but this was mainly to see if the concept would work. I may have to have a little better oscillator driving the clock module for stability. I'll have to see here, but I think for now I will end this video and maybe have a final video later on. If I get this thing all together and get it on the air, I may have another video. So anyway, that's it for this one. I hope you enjoyed it, and keep experimenting out there. Thanks for watching. See you in the next one. Bye for now.